Video number 2 of chapter 7. We are going to continue on with our idea of sampling distributions. Uh, can any sample statistic, a sample mean, a sample proportion, a sample standard deviation, a sample whatever, can it be used to estimate its population parameter? For example, can a sample mean be used to estimate the population mean? Can the sample minimum be used to estimate the population minimum? And the quick answer is unfortunately not. Some things can be good estimators, and some things just really aren't good estimators. So some statistics produce too much bias or error to closely estimate the parameter of interest. And this type of statistic is called a biased estimator. But if a statistic closely estimates a parameter with very little bias or error, then that statistic is called an unbiased estimator. Obviously, we want something that is an unbiased estimator, something that will be very close to the population parameter of interest. Now, to give you a quick rundown example of a case of it, a biased versus unbiased, before we talk about the official ones that I have in your notes here, yesterday, or in the previous video, we talked about the main idea of a sampling distribution and what it looks like and what it looks like compared to the population distribution. We noted in the first video that the sampling distribution means that they all were pretty close to the population mean. So one thing we will talk about later in this video is that the sample mean, x bar, is a good estimator of the population mean, mu, because it's close to it, okay? So that gives you an idea of what a unbiased estimator looks like. Also yesterday, or in the previous video, we talked about the standard deviation. But what we noticed about the standard deviation was as our sample size increased, our standard deviation decreased, and it got further and further away from the true population standard deviation. So can we use standard deviations to closely estimate the population standard deviation? The quick answer is no, because these numbers aren't anywhere close to the population standard deviation. So the sample standard deviation is not a good estimator. It is a biased estimator of the population standard deviation. Now, the main idea here, how do we know if a statistic that is being used as a parameter estimator is biased or unbiased? Well, a statistic is unbiased if the center of its sampling distribution is approximately the same as the population parameter. And so I will show you very specific examples of a biased and an unbiased estimator. So first off with our means, and I just mentioned earlier that means are unbiased estimators. So what I've got here is a population distribution of heights, okay? And I have a very small population, okay? I'm not talking about like all Americans or all whoever. We have a very small population, maybe one classroom size. My board would stop being all crazy on me here. Come on, board, stop it. And I know that the mean, mu, is 66.07 of this distribution. Seriously, board, I'm getting real tired of your, yeah, I can't really say stuff in here. But if I started taking samples of size 4, geez, oh Pete, if I started taking samples of size 4 from this population, and I figured out what the average height is, what we again notice is that the spread, the standard deviation starts to shrink in, right? What we notice is that the center should be about the same, and that our shape starts to get more and more approximately normal. And we can kind of tell it does, right? This stuff starts moving in, and we start seeing that bell-shaped curve. Now, just based on me taking samples of size 4, calculating the mean, every one of these dots represents a x bar, a sample mean based on 4 people from this population. And the mean of my means, and this is going to be kind of a weird way of phrasing this, but it's the mean of my sample mean. So we're going to call this mu sub x bar. So the mean of all my sample means is 65.67. And what we notice is that 66.07 and 65.67, they're kind of close to each other, right? They're not exactly the same, but they're relatively close. This could be used to estimate pretty closely what the population mean is. So is the mean an unbiased estimator? And yes, we would conclude that the mean really is an unbiased estimator. The mean of all the sample means is pretty close to the population mean. Now, what about a biased estimator? So what if we took this same population of heights, but now instead of calculating the mean heights of samples of size 4, what if I took a sample of 4 people from the population and I calculated the range, the max minus min? Well, based on my population, I know the range is 21, right? Because my max here is at 75, the min is at 54. So 75 minus 54 gives me 21. So what if I were to take samples of size 4, find the sample range from each of those, and just do that a bunch of times? And look at this distribution. This is the sampling distribution. And it's not really doing what we talked about that should happen in video 1. This doesn't look more approximately normal like this does. This is still pretty spread out compared to this. And I don't really know if the center of this distribution is about the same as this. So if I took the mean, mu, sub sample ranges, since I don't really have a symbol for sample ranges, the mean of all the sample ranges up here is 10.12. We're looking at like right here is where the center is, where before the range was 21. So if the range is really an unbiased estimator, then the mean of all the sample ranges should be really close to the population range. So is 10.12 close enough to 21? And we would have to say no. It's over half of the away from it. So the range is not an unbiased estimator. It is full of bias. We are over 50% off here from being able to take our 10.12 best guess and trying to match it up to what was true about the population range. Okay? So we're going to talk about two specific sample statistics, one being the mean and the other one being the sample proportion, p hat. Both of those are going to be unbiased estimators. And those are the only two things we will discuss really throughout the whole second semester. So we won't be doing any kind of sampling distributions with standard deviations or means or really anything but the mean and proportions. Now, we talked about bias and being an unbiased versus biased estimator, and we've talked about some variability before. So there's four real situations here regarding sampling distributions. We can either have, our ideal situation here would be number 4, that we have low bias, we have little to no error, and we have very little spread. And so if we were thinking about a target, each one of these little hits here might represent a different sampling distribution. And so it really doesn't matter what sample size we take of a sampling distribution, or if I drew a sampling distribution and you drew a sampling distribution, what we're going to find out is we're pretty close to the target overall. Okay? But this would be like if we use the sample mean or the sample proportion with a sampling distribution. We're going to be pretty close to the truth about the population. But once we start getting some biased estimators, some like situations 1 and 2 here, either we're going to have some low variability where we're all clustered together, but we're far off from the target. So if the target is the truth about the population, we're still far enough away from the truth that we're not really going to know what's going on. And what we really don't want to see happen is having high bias and high variability, where we're all just kind of all around the place here, but we're not near the truth about the population at the center of the target. Now, if you absolutely want to avoid high bias situations and you want a low bias situation, you still want to avoid high variability. We can be kind of dancing all around the center of the target here, but we need all of these dots to be more concentrated together and reduce the spread or the variability. So you might be wondering, this kind of seems like a weird situation. How can we actually apply this? Excellent question. Now, here are 4 situations that describe really these 4 target situations. And the population parameter arrow that you see in each of these situations, we're going to say this represents the truth about the population. And the histograms that you see up above here represent a sampling distribution. So we're going to match up each of these two of these words at a time, either low or high bias and high and low variability to each one of these situations. So if I want my sampling distribution to be right on the target, I can tell that this one right here, this sampling distribution, it's centered just about right on the target. Okay, so this has low bias. Okay, because it's centered right around where the arrow is. There's little to no error. Um, versus if I were to talk about this one. This one has a lot of bias in it because this is where I should be. This is where the truth is, but I'm way off the mark. I'm way over here. But what's the similarity between these two things is that both of these have low variability, right? We don't have a whole lot of spread going on here. So both of these have low variability. This one has low bias because we're right on the arrow. This one has high bias because our sampling distribution is off of the truth. Now, these two guys over here, if you haven't caught on yet, they both have high variability. They're very spread out, right? They're not very concentrated like these two were. Um, now, which one has high bias and which one has low bias? Well, I can tell this distribution right here, even though it's really spread out, it's spread out right over the arrow. So in the end, this has low bias technically because we're hitting the target of the population parameter, but we're spread out all around it. This one up here, here's where most of the observations lie. So I can tell it's got high bias. It is off the mark and it's spread out. We still have some values that are, to the right side of where we should be on the target. So here's how you can distinguish between low and high variability and low and high biasness with respect to 4 different sampling distributions. Now, the last problem here, this one is for you guys, and we will discuss this one at the beginning of class along with an additional problem very similar to this. So I'll read through it just to give you an idea here, and then you have these to answer these 2 questions on your notes. It says 4 different statistics have been proposed as estimators of a population parameter. To investigate the behavior of these estimators, 500 random samples were selected from a known population, and each statistic is calculated for each sample. Now, they didn't tell us what type of statistic they were doing, whether it was a mean or proportion or whatever the case may be. Okay? The true value of the population parameter is 75. So at 75, this is kind of like on the previous example we looked at. That's where we would normally see the arrow, right? This is where we would see this arrow. This would be at 75 specifically. So just know that 75 is where the true target is. So if you wanted to circle the 75 in all 4 of these situations, that's where we should be centered at. The graphs below show the distribution of values for each statistic. Part A is which of these statistics appear to be unbiased estimators of the population parameter, and how can you tell? Part B, which of statistics A or B would be a better estimator of the population parameter, and explain your choice. So again, I will be checking to see if you did this specific problem in your notes tomorrow. We will discuss it, and then again, we will discuss a second example, really to make sure that you understand this concept. And that is all for